What if I told you the universe isn't just a scattered collection of stars and galaxies, but a vast, interconnected web, a cosmic tapestry woven with threads of mystery? Picture this, stretching across billions of light years, invisible filaments of gas and dark matter form the backbone of everything we see, a hidden architecture so enormous it defies comprehension. These cosmic web filaments aren't just lines on a map, they're the skeleton of the cosmos, the scaffolding upon which galaxies are built, and yet they hold secrets that even the brightest minds are still struggling to unravel. Think about the last time you looked up at the night sky. Those pinpricks of light, they're not randomly placed. Each one is perched along these immense filaments like beads on a string, pulled into place by forces we're only beginning to understand. But here's the thing, these filaments are more than just cosmic highways, they're alive with unanswered questions. Why do some regions glow with unimaginable energy while others lie eerily silent? How do these threads dictate where galaxies are born, and why do some of them vanish into voids of nothingness? The deeper we look, the more mysteries we uncover, and that's exactly what we're diving into today. Over the next 25 revelations, we'll journey through the most baffling, awe-inspiring enigmas hidden within these cosmic threads. From the eerie darkness between them to the way they shape the very fate of the universe, each mystery peels back another layer of this grand design. This isn't just a story about faraway places, it's about the hidden forces that sculpted everything, including the atoms in your body. So buckle up. By the time we're done, you'll never see the night sky the same way again. To grasp the sheer scale of these cosmic filaments, imagine the universe not as a void speckled with galaxies, but as a breathing, evolving network. An intricate highway system where galaxies cluster like bustling cities connected by unseen roads. Scientists call this the cosmic web, and its filaments are more than just strands of gas and dark matter. They're the universe's architectural blueprints, dictating where galaxies form, how they move, and even how they collide. These threads stretch hundreds of millions of light years across, weaving through the cosmos in a pattern so vast it took us decades just to map a fraction of it. The story of their discovery is as fascinating as the filaments themselves. Back in the 1980s, astronomers noticed something peculiar. Galaxies weren't scattered randomly, but seemed to align along invisible lines like dew clinging to a spider's web. Supercomputer simulations later revealed these were no mere coincidences. Gravity, acting over billions of years, had sculpted the universe's matter into this intricate web-like structure, with dense strands where galaxies thrive and empty voids in between. But why does this matter? Because without these filaments, the universe as we know it wouldn't exist. They act as the universe's delivery system, funneling gas and dark matter into galaxies, fueling star formation, and even guiding colossal galaxy clusters into cosmic collisions. Picture a river nourishing a forest. The filaments feed galaxies, sustaining their growth. Yet some of these threads remain eerily dark, barely emitting any light, while others pulse with mysterious energy, as if something unseen is at work. And here's the kicker, these filaments might hold the key to the universe's biggest secrets. Dark matter, the invisible glue holding everything together, is concentrated along these strands. The way galaxies move within them could rewrite our understanding of gravity itself. Even stranger, some filaments seem to defy expectations, bending or vanishing in ways that leave scientists scratching their heads. One thing's clear, the cosmic web isn't just a backdrop. It's an active, dynamic force shaping the fate of everything we see. Among the greatest puzzles in cosmology is how these cosmic filaments, spanning billions of light years, could have formed at all. To understand their origins, we have to rewind the universe almost to its very birth. In the first moments after the Big Bang, the cosmos wasn't smooth and uniform. Tiny quantum fluctuations, smaller than an atom, created ripples in the fabric of space-time. These minuscule wrinkles in density were the seeds of everything we see today, amplified over billions of years by the relentless pull of gravity. Dark matter played a starring role in shaping these filaments. Unlike ordinary matter, dark matter doesn't interact with light, but its gravitational influence is immense. In the early universe, dark matter began clumping together first, forming vast, invisible scaffolding. Ordinary matter, the gas that would later form stars and galaxies, followed this dark matter skeleton, flowing into the densest regions and leaving behind vast, empty voids. Imagine pouring syrup onto a spider web. The syrup naturally follows the web's structure, pooling along the strands. That's how our cosmic web took shape, with galaxies strung along filaments like pearls on a necklace. But there's a twist. Recent simulations suggest these filaments didn't just form randomly. They emerged from a cosmic tug of war between gravity and the expansion of the universe. As space stretched, gravity fought back, pulling matter into these intricate, thread-like structures. Some filaments grew thicker and more massive, while others stretched thin, barely holding onto their galaxies. And here's where it gets even stranger. Some of these filaments appear to be far older or more complex than our models predict, hinting that we might still be missing a crucial piece of the puzzle. Could there have been an unseen force at work, altering the way filaments formed? Some scientists speculate that dark energy, the mysterious force accelerating the universe's expansion, might have influenced their growth. Others wonder if exotic forms of dark matter with properties we haven't yet discovered played a hidden role. What we do know is the origin of cosmic filaments isn't just a question about the distant past. It's a window into the fundamental laws that govern our universe, and every new discovery brings us closer to rewriting the story of how everything came to be. If dark matter were visible to our eyes, the night sky wouldn't just be dotted with stars. It would glow with an intricate lattice of shadowy threads, a ghostly framework binding the cosmos together. This invisible substance doesn't just lurk in the voids between galaxies. It's the hidden architect of the cosmic web, sculpting filaments with a gravitational grip so powerful it defies everything we know about physics. Yet here's the paradox: despite making up roughly 85% of the universe's matter, we've never directly seen it, not a single particle. So how do we know it's there? Because without dark matter's gravitational pull, those colossal filaments and the galaxies they cradle would simply fly apart. The evidence is written in the motions of stars and galaxies. Take the Coma Cluster, a swarm of thousands of galaxies bound together by gravity. When astronomers first measured their speeds, they found something shocking. The galaxies were moving so fast that, according to the laws of physics, the cluster should have torn itself apart long ago. Unless, of course, there was something else there, something invisible adding enough mass to hold everything together. That's dark matter's signature, an unseen hand pressing down on the scales of the cosmos. But dark matter's influence goes beyond just anchoring galaxies. Simulations show that filaments wouldn't exist without it. In the early universe, ordinary matter, the stuff we're made of, was too hot and energetic to collapse into structures on its own. Dark matter, unaffected by light or heat, clumped together first, creating gravitational wells that drew in gas and dust like cosmic whirlpools. Over billions of years, these tendrils of dark matter grew into the filaments we see today, with galaxies strung along them like lights on a wire. Yet the deeper we look, the stranger dark matter behaves. Some filaments appear to contain far more mass than their visible galaxies can account for, as if dark matter is pooling in ways we don't expect. Others seem to bend or warp, suggesting interactions we can't yet explain. And then there's the eerie case of the dark galaxy, Dragonfly 44, a massive object made almost entirely of dark matter, with so few stars it's nearly transparent. Discoveries like these hint that dark matter might not be a single substance but a family of particles, some behaving differently than others. The biggest question, though, isn't just what dark matter is. it's how it shapes the destiny of the cosmic web. Some theories suggest these filaments could be highways for dark matter, funneling it into galaxies and fueling their growth. Others propose that dark matter's distribution might hold clues to the universe's ultimate fate. One thing's certain, until we unravel this mystery, our understanding of the cosmos will remain incomplete, because dark matter isn't just hiding in the shadows, it's pulling the strings of reality itself. One of the most baffling contradictions in modern cosmology isn't about dark matter. It's about the stuff we should be able to see. The universe's filaments are supposed to be brimming with ordinary matter: protons, neutrons, and electrons, the building blocks of stars, planets, and us. Scientists call this baryonic matter, and according to our best calculations, nearly half of it is missing. Poof, gone, no one knows where. This isn't a small accounting error. We're talking about enough matter to build trillions of galaxies just vanished. The math is solid based on the cosmic microwave background. We know exactly how much baryonic matter the universe should contain. Yet when we tally up all the visible galaxies, gas clouds, and dust, we come up disturbingly short. Where could it be hiding? The leading suspect, those vast cosmic filaments, where matter is so diffuse it slips right past our telescopes. Detecting this missing matter is like trying to spot a whisper in a hurricane. The gas in filaments isn't just sparse, it's scorching hot, heated to millions of degrees by the gravitational pull of dark matter. At those temperatures, it doesn't emit visible light, only faint X-rays. For decades, our instruments weren't sensitive enough to catch these whispers. Then, in 2017, astronomers finally got their break. Using a technique called the Sunyaev-Zeldovich effect, they observed how this hot gas subtly distorts the cosmic microwave background, the afterglow of the Big Bang. The data revealed a faint, glowing haze along filaments, like tracing the outline of a shadow. But the mystery only deepens from there. Even with these detections, we're still missing about 30 to 40% of the expected baryonic matter. Some could be floating in even hotter, more diffuse gas, invisible to current X-ray telescopes. Others theorize it might be locked in exotic forms, perhaps primordial black holes or vast clouds of rogue planets drifting between galaxies. There's even a wilder idea that some of this matter has decayed into unknown particles over billions of years, leaving behind a ghostly trail we can't yet detect. What makes this puzzle so urgent is that baryonic matter isn't just filler. It's the raw material for everything we see. If we can't account for it, our models of galaxy formation, cosmic evolution, even the fate of the universe could be fundamentally flawed. Every new telescope, from the upcoming Athena X-ray Observatory to advanced radio arrays, is hunting for these lost atoms. Because until we solve the case of the missing baryons, we're not just missing matter, we're missing a crucial chapter in the story of the cosmos. Why do some cosmic filaments blaze with the heat of a million suns, while others are colder than the void of space itself? This staggering temperature difference isn't random, it's a cosmic fingerprint, revealing the violent history of galaxy formation and the invisible forces shaping our universe. Picture a filament near a bustling galaxy cluster. Here, temperatures can reach tens of millions of degrees, hot enough to vaporize any known material. Yet just a few 100 million light-years away, another filament might hover just above absolute zero, a frigid ribbon in the cosmic dark. The secret lies in what astronomers call cosmic feedback, a tug of war between creation and destruction. When galaxies form inside filaments, they don't just passively grow, they unleash torrents of energy. Supermassive black holes at their cores spew jets of plasma at near light speed, while supernovae explode like cosmic bombs, heating the surrounding gas to unimaginable temperatures. This energy doesn't just vanish, it floods the filament, turning it into a seething cauldron of charged particles. Meanwhile, in quieter regions, far from the chaos of galaxies, filaments remain cold and pristine, undisturbed for billions of years. But there's a twist. Some scorching filaments exist in near-total isolation, with no nearby galaxies to explain their heat. Here, scientists suspect dark matter plays a role. Dense knots of dark matter within these filaments might generate shock waves as they pull in gas, creating heat through sheer gravitational friction, like rubbing your hands together on a cosmic scale. Other filaments mysteriously lose heat over time, as if something is siphoning their energy away. Then there's the puzzle of the cold flows. In the early universe, some filaments remained icy highways, funneling gas directly into young galaxies without heating up. These cold streams are thought to have fueled the birth of the first galaxies, yet we've never directly observed one. Why? Because today's universe is too noisy, too filled with heated gas from later cosmic drama. Finding one would be like hearing a single whisper in a thunderstorm, but new telescopes like the James Webb Space Telescope are searching for these ghostly relics. What makes this temperature paradox so critical is its connection to life itself. Too much heat and galaxies starve. The gas needed to form stars gets blown away. Too little and galaxies might never ignite. These filaments aren't just temperature gradients, they're cosmic thermostats, fine-tuning the universe's ability to create stars, planets, and ultimately us. And somewhere in this balance between fire and ice, the universe hides its next great secret. Somewhere in the depths of space, hidden behind the Milky Way's dust and stars, lies a gravitational mystery so powerful it's dragging thousands of galaxies toward it at unfathomable speeds. Astronomers call it the Great Attractor, a colossal concentration of mass so immense it bends the very fabric of the universe around it. But here's what's even more mind-bending. The Cosmic Webs filaments might be acting as invisible highways, funneling galaxies straight into its grasp. Think of it like a cosmic river current. Just as water flows along the path of least resistance, galaxies slide along these vast filaments guided by gravity's pull. The Great Attractor sits at a junction where multiple filaments converge, a gravitational whirlpool in the intergalactic void. Measurements show our own Milky Way, along with the entire local group of galaxies, is racing toward it at over 600 kilometers per second. That's fast enough to cross the United States in less than 10 seconds. Yet, despite its obvious influence, we still don't fully understand what the Great Attractor is. Part of the challenge is its location. It lies in what astronomers call the zone of avoidance, an area obscured by our own galaxy's dense disk of gas and dust. Early X-ray observations revealed a massive cluster of galaxies at its core, but the numbers didn't add up. There wasn't enough visible matter to explain such a strong gravitational pull. Then, in 2016, radio telescopes pierced through the cosmic fog, uncovering something even larger. The Vela supercluster, a sprawling network of galaxies that could account for some of the missing mass. But even that might not be the whole story. Here's where filaments throw us another curveball. Simulations suggest these threads don't just passively guide galaxies, they amplify the Great Attractor's pull. As galaxies travel along filaments, they gain momentum, like a roller coaster picking up speed on a downhill slope. By the time they near the attractor, they're moving too fast to escape. Some researchers believe there could be even larger structures at play, like the mysterious dipole repeller, a vast cosmic void pushing galaxies toward the attractor like a pendulum swing. What makes this so unnerving is the scale of the unknown. If the Great Attractor's true nature remains hidden, what else might be lurking along these filaments, warping the motion of galaxies in ways we can't yet see? Some theories propose exotic possibilities: primordial black holes from the early universe, concentrations of dark matter we can't detect, or even flaws in our understanding of gravity itself. Whatever the answer, one thing's clear: the cosmic web isn't just a map of the universe. It's a dynamic, living system, and the Great Attractor might just be the first clue to forces we've only begun to imagine. Hidden within the faint glow of cosmic filaments lies another layer of mystery, threads of magnetism so powerful they could realign compasses across entire galaxies, if only we could see them. These magnetic fields, stretching millions of light years along the cosmic web, shouldn't exist according to classical physics. Yet here they are, woven into the fabric of the universe like invisible wires carrying currents we don't fully understand. How do magnetic fields usually associated with stars or planets end up spanning such unimaginable distances? And what role do they play in the fate of galaxies caught in their grip? The answer starts with chaos. When galaxies collide or black holes spew jets of charged particles, they unleash turbulent waves of plasma into the surrounding filaments. Like stirring a cup of coffee with a spoon, these motions generate electric currents, which in turn produce magnetic fields. But here's the twist: once created, these fields don't just fade away. Simulations show they can self-sustain, growing stronger over billions of years as they're stretched and twisted by the filament's flow. It's as if the universe has its own electromagnetic loom, quietly weaving energy into the voids. These fields aren't just cosmic decoration, they shape how galaxies form and evolve. Charged particles trying to cross a magnetized filament get deflected, like a car hydroplaning on a wet road. This can slow down the gas feeding young galaxies, starving them of the material needed to birth stars. In other cases, magnetic fields might act as cosmic scaffolding, guiding gas into dense knots where galaxies ignite. The Whirlpool galaxy, for example, shows eerie spiral patterns in its magnetic field that mirror the nearby filaments, suggesting an invisible hand helped sculpt its structure. Yet some filaments flaunt magnetic fields far stronger than any galaxy collision could explain. Deep in the Boötes void, astronomers detected a filament with a magnetic field 1,000 times more intense than our Milky Way's. No nearby galaxies or black holes could account for it. One radical theory suggests these fields might be primordial leftover from the universe's birth, frozen into the cosmic web like fossils in amber. If true, they'd be the oldest magnetic structures in existence, offering a direct glimpse into the conditions just moments after the Big Bang. The real puzzle, though, is how these fields interact with dark matter. Some filaments exhibit strange bends and kinks that align with magnetic hotspots, as if invisible forces are at work. Could dark matter particles carry a hidden electromagnetic charge? Or are these fields shaping dark matter's distribution, creating feedback loops we've yet to untangle? Every new observation peels back another layer, revealing a universe far more electrifying and enigmatic than we ever imagined. These cosmic filaments might look eternal, stretching indifferently across the void, but don't be fooled. Like everything in the universe, they have a lifespan. The question is, do they fade gently into the dark, or do they transform into something even stranger? The answer could rewrite our understanding of how the cosmos evolves. Take a single filament, one of the universe's great highways for galaxies. For billions of years, it funnels gas and dark matter, feeding the growth of galaxies along its length. But gravity is a double-edged sword. As galaxies grow heavier, their collective pull starts to warp the filament itself. Some regions thicken into dense knots, while others stretch thin, like taffy pulled too far. Simulations show that over time, the busiest filaments, those near galaxy clusters, can snap under the strain, collapsing into sprawling node points where galaxies merge in spectacular collisions. Meanwhile, quieter filaments drifting through cosmic voids might simply dissipate, their gas scattering into the abyss as dark matter's grip weakens. Then there's the dark energy wildcard. As the universe expands faster and faster, the space between galaxies widens, stretching filaments like rubber bands. Some researchers argue this could tear them apart within tens of billions of years, leaving behind isolated islands of galaxies drifting in darkness. Others believe filaments are more resilient, that their dark matter cores act like cosmic shock absorbers, holding them together even as space itself stretches. There's even a radical idea that filaments might regenerate, drawing in new gas from the voids to replenish what's lost. But here's the twist: we've already caught filaments in the act of dying. In 2022, astronomers spotted a filament near the Pisces Cetus supercluster that seemed to be unraveling, its gas glowing faintly as it bled into space. Yet in the same region, younger filaments shone bright with newborn galaxies, proof that while some threads fade, others take their place. It's a cosmic cycle of renewal, hinting that the web might never truly vanish, only change form. What's at stake isn't just the fate of these structures, but the destiny of everything they hold. If filaments dissolve too soon, galaxies could starve, cutting off the flow of gas needed to birth new stars. If they last too long, they might funnel entire galaxy clusters into collisions so violent they remake the local universe. And if dark energy's influence grows, these threads could one day be all that's left, ghostly highways in an otherwise empty sky, the last remnants of a web that once bound the cosmos together. At the edges of cosmic filaments, where the bustling highways of galaxies give way to the silent emptiness of voids, something strange happens. A frontier where the laws of physics seem to rewrite themselves. These boundary zones aren't just arbitrary lines on a cosmic map. They're battlegrounds between two extremes: the dense, chaotic energy of the filaments and the eerie stillness of the voids, where matter is so sparse it's practically a vacuum. The transition between them isn't smooth. It's a violent, turbulent clash, and what happens there could hold the key to understanding how the universe structures itself. Take the Boötes void, a colossal emptiness spanning 330 million light-years. On one side, galaxies stream along a filament like cars on a freeway. On the other, there's almost nothing, just a handful of lonely galaxies drifting in the dark. Crossing this border is like stepping from a crowded city into a desert. The density of matter drops by a factor of 1,000 in less than 50 million light-years, a gradient so steep it defies conventional models. Gas trying to flow from the filament into the void doesn't just slow down, it slams into an invisible wall, creating shockwaves that ripple back into the cosmic web. These void fronts glow faintly in X-rays, the last cries of matter struggling against the emptiness. But here's the puzzle: some boundaries are razor-sharp, while others blur like ink in water. Simulations suggest dark matter is the unseen sculptor here, its gravitational tendrils acting like a sieve. In regions where dark matter is densely packed, it funnels ordinary matter into the filament, leaving the void nearly barren. Where dark matter thins, the boundary softens, allowing tendrils of gas to leak into the void like smoke curling into still air. Yet even this explanation hits a wall when we study places like the KBC void, where the transition zone is oddly asymmetrical, as if something or someone took a bite out of the filament's edge. The most haunting mystery, though, is what happens to galaxies caught in these borderlands. Some spiral madly, their shapes distorted by tidal forces as they're pulled between the filament's gravity and the void's indifference. Others simply stop. Their stars age in isolation, their gas too diffused to form new ones, turning them into cosmic fossils. A few even get flung into the void entirely, ejected by gravitational slingshots, celestial nomads with no home to return to. And then there's the energy. At some boundaries, astronomers have detected faint but persistent radio emissions, as if the void itself is pushing back. One theory suggests these could be the ghosts of ancient galaxies, their remnants ionizing the sparse gas at the edge. Another posits that dark energy, the force accelerating the universe's expansion, might be more potent in these transitional zones, subtly warping space-time in ways we don't yet understand. What makes these borders so critical is their role in the universe's evolution. They're not passive, they're active filters, deciding which galaxies thrive and which fade into obscurity. They might even hold clues to the ultimate fate of the cosmic web itself, because if one thing's certain, it's this: where the universe's threads meet the nothingness, the rules are anything but ordinary. The gas inside cosmic filaments doesn't flow smoothly. It churns like a stormy ocean, twisting and colliding in ways that baffle even the most sophisticated supercomputer simulations. These rivers of superheated plasma, some wider than entire galaxy clusters, should, in theory, behave predictably, following the laws of fluid dynamics we've studied for centuries. But the universe loves to defy expectations. Instead of orderly currents, we see turbulence so extreme it shreds gas clouds into fragmented wisps, sending shockwaves racing along filaments at thousands of kilometers per second. Recent simulations from the Illustris TNG project revealed just how chaotic these environments are. When researchers modeled filaments at the highest resolution yet, they found vortices forming within the gas, massive whirlpools spanning millions of light years. Some regions became so turbulent that gas particles collided with enough force to create bursts of X-rays, while elsewhere magnetic fields twisted the plasma into braided helical structures like cosmic DNA. The most surprising discovery: these dynamics aren't random. They follow fractal patterns, repeating the same chaotic motifs at vastly different scales, from the width of a solar system to the length of a filament itself. But simulations only tell half the story. Observations from the Chandra X-ray Observatory caught this chaos in action. One filament near the Perseus cluster showed gas temperatures fluctuating wildly, pockets scorching at 50 million degrees Celsius right next to cooler regions at just 10 million degrees. Even stranger, the gas wasn't mixing as expected. Instead, it clumped into dense knots and thin streams, as if an unseen force was sorting it like sand through a sieve. The prime suspect: dark matter's gravitational tides. As gas flows along filaments, it passes through invisible knots of dark matter, regions where the gravitational field intensifies abruptly. These knots act like cosmic boulders in a river, creating wakes of turbulence that ripple downstream. Another factor might be the ghosts of ancient supernova explosions so powerful their remnants still echo through the gas billions of years later, stirring it like a spoon in a cup. Yet the biggest shock came in 2023, when the XRISM satellite detected gas spinning along a filament's axis like a colossal screw. This rotation shouldn't be possible on such scales. There's no known force that could set an entire filament spinning. Some theorists suggest it's a relic from the universe's birth, a remnant of primordial vortices spun up by the Big Bang itself. Others argue it's evidence of something even weirder: large-scale magnetic fields twisting the gas into motion, like an invisible hand stirring a pot. What makes this turbulence so consequential is its role in galaxy formation. Calm, steady gas flows would feed galaxies smoothly, creating orderly spirals like the Milky Way. But chaotic filaments deliver gas in violent bursts, triggering starbursts or supermassive black hole eruptions. Some galaxies might drown in these tempests, while others are born from them. One thing's clear: the universe doesn't build galaxies on a quiet assembly line. It forges them in the storm. Among the swirling gas and dark matter of cosmic filaments, there could be predators lurking in the shadows, black holes untethered from galaxies, drifting silently through these intergalactic highways. These aren't the supermassive beasts we're used to, anchored at the hearts of galaxies. These are rogue black holes, some as massive as 1,000 suns, others as small as a city, ghosting through the cosmic web without a trace. And the terrifying truth: we might never see them coming. Black holes are already cosmic ninjas. By definition, they don't emit light. The only way we detect them is by their influence on nearby objects, the way they warp starlight, the X-ray screams of gas spiraling into their mouths, or the gravitational waves they unleash when colliding. But isolate one in the near-perfect vacuum of a filament far from stars or gas clouds, and it becomes nearly invisible. No accretion disk, no violent flares. Just pure, unchallenged gravity moving through the darkness like a wolf through fog. Yet the clues are there. Some filaments exhibit strange, localized gravitational aberrations, regions where the tug of dark matter doesn't quite account for the way galaxies are being nudged. In 2019, astronomers studying the Laniakea supercluster found a filament where galaxies were being subtly pulled toward an unseen point, as if an invisible hand were dragging them. The math suggested a compact object roughly 20,000 times the mass of our Sun, but when they pointed every telescope they had at the spot, nothing. No light, no radiation, just gravity's fingerprint. Then there's the case of the runaway quasars. A handful of active galactic nuclei, supermassive black holes spewing jets of energy, have been found oddly displaced from their host galaxies. One theory suggests these could be the aftermath of galactic collisions, where black holes were flung into filaments like billiard balls. If true, there could be thousands more out there drifting silently, their feeding frenzies long over. But the most unsettling possibility, primordial black holes theorized to have formed in the chaos of the Big Bang itself. These ancient relics could range from the mass of a piano to 1,000,000 suns, and filaments, with their dense dark matter, might be the perfect traps to collect them. Some researchers even speculate these could be the elusive dark matter we've been searching for, their combined gravity shaping filaments from within. The real danger isn't that these rogues might wander into our neighborhood. Space is too vast for that. It's what their existence would mean for our understanding of the universe. If black holes pepper the cosmic web, they could be secretly seeding galaxies, warping the paths of entire clusters, or even distorting the filaments themselves. And until we develop gravity wave detectors sensitive enough to catch their whispers, they'll remain cosmic phantoms hiding in plain sight, rewriting the rules from the shadows. Some filaments in the cosmic web shimmer with an eerie, ghostly light, while others vanish into perfect darkness, a stark contrast that shouldn't exist if these structures were as uniform as we once thought. The difference isn't just a cosmetic quirk, it's a cosmic clue pointing to hidden forces shaping the universe in ways we're only beginning to decode. The secret lies in the delicate dance between ionized gas and an invisible sea of radiation bathing the cosmos. Picture a filament as a vast river of hydrogen gas, thin and diffuse. Under normal conditions, this gas would be completely transparent, invisible to our telescopes. But when blasted by ultraviolet light from distant quasars or young galaxies, something remarkable happens. The radiation strips electrons from the hydrogen atoms, ionizing them and causing the gas to emit a faint glow like neon signs lighting up in a dark alley. This is the cosmic UV background, a pervasive fog of high-energy photons left over from the universe's early epochs, still echoing through space billions of years later. Yet not all filaments catch this light the same way. Some, like the Lyman alpha filaments near massive galaxy clusters, blaze with luminosity, their gas so ionized they resemble celestial auroras. Others, particularly those in quieter cosmic neighborhoods, stay stubbornly dark. The key factor, proximity to cosmic powerhouses. Filaments threading through regions packed with galaxies or quasars get bombarded by intense radiation, turning their gas into glowing plasmas. Those drifting through emptier voids, shielded from the UV onslaught, remain shadowy and cold. But here's where it gets strange. In 2021, the Keck Observatory spotted a filament glowing softly in the middle of nowhere. No nearby galaxies, no quasars, nothing to explain the light. The glow was too uniform to come from a single source, suggesting something far more exotic. The filament might be acting like a giant fiber optic cable, trapping and scattering UV radiation along its length. If true, it means these structures aren't just passive components of the cosmic web, they're active participants, channeling energy across unimaginable distances. The real mystery, though, is why some filaments refuse to glow at all. Even in regions flooded with UV light, certain threads stay dark, as if their gas is locked in some unseen state. One theory points to dense pockets of molecular hydrogen, which absorb UV radiation without re-emitting it. Another wild possibility involves magnetic fields so strong they suppress ionization entirely, creating cosmic shadow zones where light goes to die. What makes this puzzle so captivating is its connection to the universe's evolution. Ionized filaments act as cosmic recycling plants, their glowing gas cooling and collapsing into new galaxies. Dark filaments, meanwhile, might be cosmic graveyards, places where gas stays trapped in limbo, unable to form stars. Together, they paint a picture of a universe where light and shadow aren't just aesthetics, they're the architects of reality itself. And somewhere in that interplay, the next great cosmic revelation might be hiding. Stretching nearly 1.5 billion light-years across the cosmos, the Sloan Great Wall isn't just another filament, it's a cosmic titan so vast it defies everything we thought we knew about how the universe organizes itself. Discovered in 2003 by scientists mapping galaxy distributions in the Sloan Digital Sky Survey, this structure isn't just big, it's impossibly big. A gargantuan ribbon of galaxies and dark matter that shouldn't exist under our current understanding of cosmic evolution. The problem lies in scale. According to the cosmological principle, a cornerstone of modern astrophysics, the universe should look roughly the same in all directions at large enough scales. No single structure should dominate. Yet the Sloan Great Wall does exactly that, spanning nearly 1/10 of the observable universe's radius. To put that in perspective, if our Milky Way were the size of a coffee cup, this filament would stretch from New York to Los Angeles. Such colossal architecture throws a wrench into our models, which predict that gravity simply wouldn't have had enough time since the Big Bang to sculpt something so immense. But is it truly a structure or just a trick of perspective? Skeptics argue it might be a chance alignment, multiple smaller filaments stacked along our line of sight like cosmic highway lanes merging in the distance. Yet detailed redshift measurements tell a different story. The galaxies within the wall share nearly identical velocities, suggesting they're genuinely bound together by gravity, not just an illusion. Even stranger, the wall isn't uniform. It's patchy, with dense galaxy clusters strung along it like pearls, separated by near-empty gaps wider than some superclusters. The real shock came when simulations tried to recreate it. Even with dark matter's gravitational boost, no virtual universe could spontaneously grow a filament this size without breaking known physics. Some theorists suggest an exotic explanation: primordial quantum fluctuations in the early universe might have seeded ultra-rare, overdense regions that ballooned into these monsters. Others propose our understanding of dark energy's role in structure formation is incomplete, that its repulsive force might have somehow sculpted the wall by pushing matter into these vast ribbons. Then there's the timing problem. The Sloan Great Wall appears too mature for its age, its galaxies too clustered and evolved for a structure supposedly forming in a universe only 13.8 billion years old. It's as if we dug up a fossilized skyscraper in a prehistoric swamp. The pieces shouldn't fit. Could there have been an earlier, unknown phase of cosmic acceleration that let structures like this form faster? Or does the wall hint at something even more unsettling, that our observable universe is just a tiny fragment of a far grander, inhomogeneous cosmos where such giants are common? What makes this mystery so pivotal is its stakes. If the Sloan Great Wall is real, it could force us to rewrite our theories of galaxy formation, dark matter, even the Big Bang itself. If it's a fluke, we need to explain why our corner of space seems to break the rules. Either way, one thing's certain: this cosmic colossus isn't just a curiosity. It's a challenge written across the sky in galaxies and shadows, waiting for us to unravel its secrets. Galaxies aren't scattered randomly along cosmic filaments. They gather in perplexing clumps, like beads strung unevenly on an invisible thread. This beads on a string pattern isn't just a cosmic coincidence. It's a fingerprint of the universe's hidden physics, revealing how gravity, dark matter, and even the echoes of the Big Bang itself conspired to shape the cosmos. But why do some filaments host dense galaxy clusters every few million light-years, while others stretch barren for vast distances, their galaxies sparse and lonely? The answer might rewrite our understanding of how the universe builds its largest structures. Take the Coma supercluster's filament, a bustling highway of galaxies. Here, massive clusters like the Coma cluster and Leo cluster glow like streetlights along a dark road, each packed with thousands of galaxies. Yet between them lie near desolate stretches where only a handful of dwarf galaxies drift. This isn't unusual. Similar clustering appears across the cosmic web, from the Perseus-Pisces filament to the Hercules Corona Borealis Great Wall. The pattern is too consistent to be chance, but too irregular to fit neatly into our simulations. The leading theory points to Baryon acoustic oscillations, pressure waves from the early universe that rippled through the primordial plasma like sound waves in water. These waves left behind dense regions where matter clumped together, seeds that eventually grew into today's galaxy clusters. But here's the twist. Dark matter seems to have amplified these clusters in ways we didn't predict. Supercomputer models show dark matter knots forming along filaments, their gravitational pull funneling gas and galaxies into tight bundles like toll booths on a cosmic freeway. Yet some knots attract far more matter than others, creating those unevenly spaced beads. Even stranger, the spacing between clusters isn't random, it follows a rough rhythm. In many filaments, dense clusters recur every 150 to 200 million light-years, a scale that eerily matches the original Baryon oscillations. It's as if the universe's first vibrations still resonate today, their echoes frozen into the distribution of galaxies, but not all filaments play by these rules. The Boots void filament, for example, shows almost no clustering, its galaxies scattered thinly like breadcrumbs dropped along a path. Why? One possibility is that dark energy's repulsive force stretched some filaments too thin, preventing clusters from forming. The implications are staggering. If galaxy clustering depends on these ancient oscillations, then the spacing between clusters could act as a cosmic ruler, helping us measure the universe's expansion rate with unprecedented precision. But the outliers, the filaments that defy the pattern, might hint at something even bigger, unknown forces beyond dark matter and dark energy, sculpting the cosmic web in ways we've yet to imagine. And then there's the mystery of the orphan clusters. Some galaxy groups sit isolated along filaments far from the main beads, as if they were tossed aside by some cosmic upheaval. Were they ejected during ancient collisions, or do they mark regions where dark matter's grip faltered? Every thread of the cosmic web holds clues, and each uneven cluster is a piece of a puzzle we're only beginning to assemble. One thing's certain: the universe doesn't string its beads at random. There's a design here, written in gravity and shadow, waiting to be read. Stretching across the universe's grand tapestry, the cosmic web's filaments appear to connect everything, yet when we map them in detail, something unsettling emerges. Giant gaps slice through these threads like broken bridges, leaving galaxies stranded in islands of darkness. Are these missing links simply regions too faint for our telescopes to see, or do they point to something far stranger, cosmic voids so profound they tear the web itself apart? The challenge begins with observation. Even our most advanced telescopes struggle to detect the faintest filaments, especially those drifting through the emptiest corners of space. Gas in these threads can be so diffuse that a single cubic meter might hold just a few atoms, far emptier than any vacuum we've created on Earth. When the Hubble Space Telescope peered into the empty space between two filaments in the Boots void, it found nothing. No gas, no galaxies, just a staggering void spanning 60 million light-years. Was this a true absence, or had the filament's gas cooled into some invisible form, like rogue dark matter or primordial hydrogen we can't yet detect? Yet some gaps defy even these explanations. In 2020, astronomers studying the Laniakea supercluster noticed a filament that simply stopped on one side. Galaxies streamed along the thread in perfect formation. On the other, nothing, no gradual thinning, no fading, just a clean break, as if someone had snipped the cosmic thread with scissors. Intriguingly, this rupture aligned with a region where gravitational lensing measurements hinted at an immense concentration of dark matter. Could something be hiding there, warping the filament structure? One radical theory suggests these gaps might be scars from ancient cosmic collisions, where filaments were severed by the gravitational shockwaves of supercluster scale impacts billions of years ago. Then there's the timing problem. Simulations predict filaments should form a near-continuous web with few truly empty gaps. Yet the observed universe shows far more fragmentation than our models allow. Some researchers argue this points to flaws in our understanding of dark matter's behavior. Perhaps it clumps differently on vast scales, leaving voids where gravity's grip weakens. Others propose a wilder idea, that these gaps are evidence of cosmic defects, remnants of phase transitions in the early universe, like cracks in ice as it freezes. The most haunting possibility that these missing links aren't empty at all. Radio telescopes have detected faint, unexplained emissions from some void regions, too diffused to be galaxies, yet too structured to be noise. Could there be an invisible form of matter or energy threading these gaps, something our current physics can't describe? Or worse, what if the gaps are growing, their edges fraying as dark energy stretches the web to its breaking point? Every unanswered question is a reminder the cosmic web isn't just a map of what we see. It's a puzzle with pieces we're only beginning to touch. The idea that cosmic filaments, threads of gas and dark matter spanning hundreds of millions of light years, could be spinning sounds like science fiction. Yet a growing number of astronomers are staring at data that suggests exactly that. If true, it would upend our understanding of how the largest structures in the universe behave, forcing us to rewrite the rules of cosmic evolution. Take the case of filament W1, a colossal thread weaving through the Pisces Cetus supercluster. In 2023, the European Space Agency's XMM Newton telescope detected something bizarre. The gas on one side of the filament was blue-shifted, moving toward us, while the other side redshifted, pulling away. The simplest explanation, rotation. Like a gargantuan DNA strand, the entire structure might be twisting along its axis, completing one full revolution every 8 billion years. That's slow by human standards, but staggering for something so immense. The energy required to set such a behemoth spinning defies conventional physics. Critics argue it's a trick of perspective, perhaps two smaller filaments, each moving independently, aligned in a way that mimics rotation. But simulations from the Illustris TNG project complicate that theory. When researchers modeled filament formation with unprecedented detail, they found that under rare conditions, dark matter vortices swirling eddies in the early universe could impart angular momentum to entire filaments. These wouldn't spin like a top, but more like a corkscrew, with matter spiraling along the filament's length. The implications are profound. If filaments rotate, they could act as cosmic flywheels, transferring angular momentum to galaxies and shaping their spins. Our own Milky Way's rotation might owe itself to a primordial twist in the filament that birthed it. Even more radical is the idea that dark matter itself could have fluid-like properties, allowing it to generate large-scale vortices. Some theorists speculate this might explain why certain galaxy clusters orbit filaments rather than falling straight into them, as if caught in a gentle whirlpool's current. Yet the biggest puzzle remains: what force could set something so vast in motion? One controversial hypothesis points to quantum fluctuations in the infant universe, amplified by inflation into macroscopic rotations. Another suggests collisions between superclusters, cosmic fender benders, might have kicked filaments into spin like a pinwheel in the wind. Until we have more observations, the question hangs in the void, a tantalizing hint that the universe's skeleton might be more dynamic than we ever dreamed. Dark energy isn't just accelerating the universe's expansion, it's playing a cosmic tug of war with the very fabric of the cosmic web. Picture a vast rubber band stretching between galaxies. Gravity tries to pull it taut, keeping filaments dense and structured, while dark energy tugs in the opposite direction, relentlessly stretching space itself. The outcome of this struggle could determine whether filaments remain the universe's backbone or dissolve into the void. For 14 billion years, gravity ruled supreme, sculpting filaments into the grand highways we see today. But around 5 billion years ago, dark energy gained the upper hand. As the universe's expansion accelerated, filaments began feeling the strain. Some, like those near massive galaxy clusters, cling to their structure gravity's grip is too strong to break. Others, especially those threading through empty voids, are stretching thin, their gas dispersing like smoke in the wind. The most fragile filaments might already be unraveling, their galaxies left adrift in ever-widening gaps. Yet dark energy's influence isn't uniform. Observations reveal bizarre patches where filaments appear to resist expansion entirely. In the Pisces-Cetus supercluster, one filament shows no sign of thinning, despite being surrounded by some of the emptiest voids in the cosmos. Simulations suggest dark matter might be fighting back here, its gravitational pull concentrated in dense knots that act like anchor points, countering dark energy's push. Elsewhere, filaments exhibit strange kinks or bends, as if space itself is warping under the competing forces, gravity's whisper versus dark energy's roar. The most chilling possibility, dark energy might not just stretch filaments, it could be rearranging them. Some models predict that in tens of billions of years, the cosmic web will transform into isolated, island universes, with filaments stretched so thin they sever entirely. Galaxies that once traveled these roads will be left marooned, their lights fading as the space between them expands faster than any signal can cross. But here's the twist, filaments might be more resilient than we thought. Recent studies of quasar light passing through distant filaments reveal subtle distortions, hinting at an unseen tension in the gas, as if dark energy's stretch is being countered by some hidden force. Could dark matter have properties we haven't accounted for, or is there another player in this cosmic game, something woven into the fabric of space-time itself? One thing's certain, the fate of the cosmic web isn't just a question about structure. It's a battle between the universe's two greatest mysteries, and the filaments are the ropes in their tug of war. Hidden in the faint afterglow of the Big Bang, there might be echoes of filaments far older than any galaxy structures so ancient they predate stars, planets, and even light itself. These primordial filaments aren't just relics of the past, they're the universe's first rough sketches, the scaffolding upon which everything we know would later be built. And the key to uncovering them lies in the cosmic microwave background, that static hiss of radiation left over from the universe's fiery infancy. The story begins just 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form, releasing a burst of light that still lingers today as the CMB. But look closer at this ancient light, and subtle temperature variations emerge, hot and cold spots no larger than 1 part in 100,000. These tiny fluctuations aren't random. They're the imprints of density variations in the early universe, regions where matter ever so slightly clumped together under gravity's whisper. And here's the astonishing part. Supercomputer simulations tracing these fluctuations forward in time reveal they didn't just form random blobs. They stretched into delicate, thread-like structures, the universe's very first filaments. What's mind-bending is how these proto-filaments differ from their modern counterparts. Without galaxies or dark matter's intricate dance to shape them, they were simpler, purer, vast rivers of hydrogen and helium gas streaming through the darkness. Some models suggest they may have formed fractal-like patterns, repeating the same branching shapes at different scales, a cosmic echo of nature's tendency toward self-similarity, from snowflakes to river deltas. Others propose they were far more dynamic, with shockwaves from the universe's initial expansion creating turbulent eddies within them, like whirlpools in a primordial river. But the real mystery lies in what happened next. As the universe expanded, these filaments should have thinned and faded, their matter dispersing into the growing voids. Yet somehow they persisted, evolving into the cosmic web we see today. How? The answer might be written in the CMB's polarization pattern swirls of light that could reveal how early filaments interacted with the universe's first magnetic fields or even exotic particles we've yet to discover. There's even a tantalizing hint from the Planck satellite's data, certain elongated anomalies in the CMB that align suspiciously well with the orientations of modern superclusters, as if the universe's skeleton was already taking shape before the first stars flickered to life. The implications are staggering. If primordial filaments left their mark on the CMB, they could help solve one of cosmology's biggest puzzles: why the universe's large-scale structure looks so eerily similar to the neural networks in our brains or the distribution of galaxies in computer simulations. It's as if the universe was always destined to weave itself into this intricate web, its blueprint encoded in those first whispers of matter. And somewhere in those ancient threads, we might just find the missing link between the Big Bang's chaos and the ordered cosmos we call home. When cosmic filaments collide, it's not a gentle merging. It's a full-scale cosmic wreck, a slow-motion disaster unfolding over hundreds of millions of years. Picture two colossal highways of dark matter and superheated gas, each wider than a galaxy cluster, slamming into one another at speeds that defy human comprehension. The shockwaves ripple across millions of light-years, reshaping galaxies, igniting bursts of star formation, and even tearing apart the very fabric of the filaments themselves. These collisions aren't rare, they're happening all across the universe, and each one leaves behind a forensic trail of cosmic chaos. Take the famous Cosmic Bullet Cluster, where two galaxy clusters collided in a spectacle so violent it sent shock fronts plowing through intergalactic gas like a boat's wake through water. But when filaments collide, the scale is even grander. Unlike galaxy clusters, which are just dense knots along filaments, these collisions involve the threads themselves, the underlying structure of the cosmic web. Simulations from the Illustris project show the aftermath: twisted, braided filaments where gases from both structures mix in turbulent whirlpools, while dark matter, unaffected by friction, slides through like a ghost, leaving behind gravitational fingerprints that warp the paths of nearby galaxies. The real carnage happens in the gas. As filaments merge, their ionized plasmas, already millions of degrees hot, compress further, reaching temperatures that can exceed 100 million degrees. At these extremes, atoms are stripped bare, emitting X-rays so intense they outshine entire galaxies. The Chandra X-ray Observatory has spotted these telltale glows at collision sites, like cosmic road flares marking the wreckage. But here's the twist: some filaments don't just heat up, they cool. In rare cases, the collision's turbulence triggers a runaway cooling effect, condensing gas into dense knots that ignite starbursts, birthing thousands of new stars in a single cosmic breath. Then there's the dark matter's role. Since it doesn't interact with light or gas, it passes through the collision unscathed, piling up in invisible clumps that warp spacetime itself. Gravitational lensing maps reveal these dark matter skeletons, tracing where the true mass of the filaments lies long after the visible gas has scattered. Some collisions even fling dark matter into rogue streams, creating gravitational anomalies that tug on galaxies millions of light-years away. But the most dramatic consequence: the rebirth of galaxies. When filaments collide, they funnel gas into the galaxies caught in the crossfire, triggering black hole eruptions and supernova on scales we rarely see. The NGC 626 galaxy, for example, sits at the intersection of two filaments, its supermassive black hole devouring material so furiously it's become one of the brightest quasars in the sky. Yet for every galaxy revitalized, another might be torn apart. Dwarf galaxies, lacking the gravity to anchor themselves, are often shredded into tidal streams, their stars scattered like crumbs along the filament's length. What makes these collisions so pivotal is their legacy. They're not destruction, they're transformation. Filaments merge and knot, creating new nodes where future galaxy clusters will arise. The gas they churn and compress becomes the raw material for generations of stars. Even the dark matter's dance reshapes the gravitational landscape, steering the universe's growth in ways we're only beginning to map. Every collision is a cosmic turning point, a reminder that the universe's web isn't static. It's alive, evolving, and constantly rewriting its own story in threads of fire and shadow. One of the most heated debates in modern cosmology isn't just about how fast the universe is expanding, it's about why our measurements refuse to agree. On one side, the Hubble Space Telescope gives us one number. On the other, the cosmic microwave background whispers another. This discrepancy, known as the Hubble tension, has left scientists scrambling for answers. But what if the cosmic webs filaments, those vast threads of dark matter and gas, are silently twisting the data in ways we never anticipated? At the heart of the tension lies a simple question: how quickly is space stretching? Measurements based on nearby galaxies using Cepheid variable stars and supernova suggest an expansion rate of about 73 kilometers per second per megaparsec. Yet observations of the early universe, particularly the Planck satellite's analysis of the cosmic microwave background, insist it's closer to 67. That difference might sound small, but over cosmic distances it adds up to a staggering rift. Some call it a crisis, others see it as an opportunity, a crack in our theories where new physics might slip through. Here's where filaments enter the picture. These colossal structures aren't just passive backdrops, they're dynamic players in the cosmos, warping the paths of light and matter alike. When astronomers measure distant supernova to calculate the Hubble constant, they assume light travels through a universe that's uniformly expanding. But filaments defy that simplicity. Their immense gravitational pull can subtly bend light beams, a phenomenon called weak gravitational lensing. More critically, they create regions where the local expansion rate isn't quite the same as the cosmic average, like eddies in a river where the water swirls instead of flowing smoothly. The game changer: filaments might be skewing our measurements without us realizing it. Imagine a supernova's light passing through a dense filament. The extra gravity slows the light's journey slightly, mimicking the effect of a faster expanding universe. Alternatively, if the filament's gas is ionized and turbulent, it could scatter the light, altering its apparent brightness and throwing off distance calculations. Recent simulations from the Millennium TNG project show these effects could account for up to a 15% discrepancy, enough to bridge at least part of the Hubble gap. But there's a wilder possibility. Some filaments, particularly those near galaxy clusters, might harbor pockets of accelerated expansion, driven by dark energy's mysterious influence. If these filaments act like cosmic accelerators, stretching space more quickly within their boundaries, they could create localized Hubble bubbles where measurements diverge from the broader universe. It's as if we've been trying to measure the speed of a highway by watching cars in a tunnel. We might not be seeing the whole road. The stakes couldn't be higher. If filaments are the hidden variable in the Hubble tension, it means our maps of the universe are missing a crucial layer of complexity. Worse, it suggests that dark energy, the force driving cosmic acceleration, might interact with large-scale structures in ways our models don't predict. Upcoming telescopes like the Vera C. Rubin Observatory are poised to test this, mapping filaments with unprecedented precision to see if their distortions align with the tension. Until then, one thing's clear: the universe's expansion isn't just a number. It's a story, and the cosmic web might be holding the pen. At the smallest scales of the universe, space-time isn't smooth. It's a seething, frothing chaos known as quantum foam, where particles flicker in and out of existence in a dance dictated by the uncertainty principle. These quantum fluctuations are tinier than atoms, fleeting as a heartbeat. But what if these microscopic fireworks aren't confined to the infinitesimal? What if their echoes ripple upward, imprinting themselves on the largest structures in existence, the cosmic filaments that bind the universe? The idea isn't as far-fetched as it sounds. Quantum foam emerges from the fundamental fabric of reality, where space-time itself is thought to churn with virtual particles and microscopic wormholes. Normally, these effects cancel out over large distances like waves smoothing into glassy water. Yet filaments aren't just any large structure. They're the universe's nervous system, threaded with dark matter and turbulent plasma, environments where gravity and quantum forces might interact in ways we've never seen. Some theorists propose that within these cosmic rivers, conditions could amplify quantum effects, twisting them into observable anomalies. Imagine a filament as a quantum antenna. Its immense length, stretching hundreds of millions of light-years, might act like a resonance chamber, capturing and magnifying quantum noise. In regions where dark matter is densely packed, its gravitational pull could warp space-time enough to freeze quantum fluctuations, stretching them into macroscopic wrinkles. These wouldn't just be mathematical quirks, they could leave tangible scars. Gas flowing through a filament might exhibit strange turbulence patterns, or X-ray emissions could flicker unpredictably, as if something beneath the surface were stirring the cosmic pot. There's even a wilder possibility: filaments as cosmic superconductors. Under extreme conditions, some theories suggest that dark matter or exotic particles could form Cooper pairs, the same mechanism behind earthly superconductivity, allowing quantum effects to propagate across vast distances. If true, filaments might host persistent currents or quantum entanglement on scales larger than galaxies, with changes at one end instantly affecting the other, defying Einstein's speed of light limit. The smoking gun: look to the voids. These empty regions between filaments are so pristine that any quantum imprint would stand out like a fingerprint on glass. If filaments are warping spacetime at quantum scales, voids might bear the marks: subtle distortions in the cosmic microwave background, or inexplicable gaps in the distribution of galaxies. Some astronomers are already scouring sky surveys for these anomalies, hunting for patterns that no classical theory can explain. What makes this speculation so electrifying is its implications. If quantum foam leaves traces in filaments, it would bridge the greatest divide in physics, the chasm between quantum mechanics and gravity. It might even hint at a deeper truth, that the universe's largest structures and smallest whispers are threads of the same tapestry, woven together in ways we're only beginning to imagine. The cosmic web isn't just a relic of gravity's pull, it could be a living quantum canvas, vibrating with the universe's oldest secrets. Deep within the swirling currents of cosmic filaments, an astonishing possibility emerges. These vast rivers of gas and dark matter might be the universe's ultimate delivery system, ferrying the very ingredients for life across unimaginable distances. Picture a filament not just as a scaffold for galaxies, but as a cosmic conveyor belt, carrying the atomic building blocks of planets, water, and even organic molecules from one corner of the universe to another. The stuff you're made of: carbon, oxygen, nitrogen could have hitchhiked across millions of light years on these invisible highways long before Earth even existed. The journey begins in the hearts of stars. When massive stars explode as supernova or colliding neutron stars unleash kilonovae, they seed space with heavy elements forged in their cores. These elements don't just drift aimlessly, they're swept up by filaments, suspended in their superheated plasma like dust in a windstorm. Simulations show that a single filament can transport these enriched gases for billions of years, channeling them into galaxy clusters where new stars and planets form. The Orion Nebula, for instance, sits at the intersection of multiple local filamentary streams. Its gas rich with complex molecules like methanol and formaldehyde, precursors to life's chemistry. But here's where it gets even wilder. Some filaments might be more than just passive carriers. In regions where gas cools sufficiently, these threads could act as cosmic chemistry labs. The Perseus-Taurus filament, observed by the ALMA telescope, contains clouds of gas chilled to just 10 degrees above absolute zero, cold enough for atoms to link into molecules. Within these frigid pockets, hydrogen bonds with oxygen to form water ice, while carbon chains evolve into polycyclic aromatic hydrocarbons, the same organic compounds found in meteorites and comets. It's as if the universe is prepping life's ingredients long before planets arrive. The real revelation came with the discovery of filament rain. In galaxy clusters like Able 268, telescopes have spotted dense gas clouds condensing out of filaments and raining onto galaxies below. These downpours aren't just water, they deliver metals, organic molecules, and even probiotic compounds like hydrogen cyanide, a key player in the origin of life. Our own Milky Way might have grown through such showers, with filaments like the Magellanic Stream still dripping gas into its halo today. Yet the greatest mystery lies in the outliers. Certain filaments, like the one threading the spiderweb galaxy, exhibit bizarrely high concentrations of phosphorus, an element critical for DNA and cell membranes. Normally rare in space, its abundance here suggests filaments might concentrate certain elements like cosmic sieves, filtering and sorting atoms by weight or charge. If true, it means life's recipe isn't just scattered randomly across the cosmos. The universe's largest structures could be quietly curating it, delivering the right ingredients to the right places at the right times. And that raises a tantalizing question. If filaments are the universe's supply chains, how many other worlds might they have fed? Traces of Earth's water have been linked to ancient asteroid impacts, but those asteroids could have formed from gas delivered by filaments billions of years earlier. The same threads weaving through the void might have woven the story of life itself, not just here but perhaps everywhere. The cosmic web isn't just shaping galaxies, it could be the silent architect of biology, turning empty space into a nursery for existence. The cosmic web's filaments have endured for billions of years, but nothing in the universe lasts forever, not even these titanic threads. As the cosmos ages, dark energy's relentless push will stretch space itself to its breaking point, and the fate of these structures hinges on a battle between gravity's grasp and the void's hunger. Will they dissolve into silence, or might they outlast the stars themselves? The answer lies in the subtle dance between destruction and resilience, a dance already playing out in the farthest corners of the observable universe. Consider the most isolated filaments first, those drifting in the emptiness between superclusters. Already, these threads are straining under the universe's expansion, their gas thinning to near nothingness. Over tens of billions of years, dark energy will stretch them so far that their atoms disperse into the void, leaving behind only ghostly trails of dark matter. Without gas to glow or galaxies to mark their presence, these filaments will vanish from sight, their only remnants faint distortions in the light of distant quasars. Yet even then, their dark matter skeletons might linger, invisible scaffolds in an ever-emptying sky. But not all filaments will go quietly. Those anchored by massive galaxy clusters like the Coma supercluster's central spine face a different end. Gravity's grip here is too strong for dark energy to sever. Instead, these filaments will contract, pulling their galaxies into ever tighter knots. Gas trapped in these regions will collide and heat to unimaginable temperatures, igniting final bursts of star formation before the fuel runs out. Eventually, the clusters themselves will merge, their black holes spiraling together in eruptions of gravitational waves, a last shout before the darkness closes in. Then there's the wild card, quantum decay. If protons, the building blocks of atoms, aren't perfectly stable, as some theories suggest, then over incomprehensible timescales, even the densest filaments will disintegrate at the subatomic level. Gas turns to radiation, dark matter particles evaporate, and the cosmic web unravels into a faint sea of photons and leptons. It's a slow, silent end where filaments don't snap or fade so much as dissolve into the quantum foam of spacetime itself. Yet against all odds, some filaments might cheat oblivion. In regions where dark matter clusters just right, its gravitational pull could counteract dark energies stretch indefinitely, creating eternal threads in an otherwise dying cosmos. These filaments would become the last large-scale structures in existence, their galaxies long dead but their dark hearts still spinning in the endless night. Future civilizations, if any survive, might huddle near them, drawing warmth from their decaying dark matter or harvesting the last whispers of gravitational energy. The cruelest irony, even if filaments persist, the universe will forget them. As expansion accelerates, light from their far ends will redshift beyond detectability, then vanish entirely as space stretches faster than photons can travel. Each filament will become its own isolated island, cut off from the rest of reality, alone in the dark. The cosmic web, once a bustling network binding the universe together, will be reduced to fractured strands, each unaware the others ever existed. But here's the haunting twist: in a way, filaments never truly die. Their matter, whether scattered atoms or lingering dark particles, remains part of the universe, cycling through cosmic epochs we can't yet imagine. Some theories suggest a cyclical cosmos, where future Big Bangs weave new webs from the ashes of the old. If so, filaments might rise again, their patterns echoing across eternity like a melody too beautiful to play just once. Until then, they'll keep shaping the universe's story, from the first galaxies to the last protons decay, silent architects of everything. What if cosmic filaments aren't just natural wonders? What if they're the universe's ultimate power grid, harnessed by civilizations so advanced they've turned the fabric of space into their playground? It sounds like science fiction, but the numbers don't lie. Filaments contain enough energy in their magnetic fields and turbulent plasma to power entire galaxies. For a sufficiently advanced species, these threads might not just connect the cosmos, they could fuel it. Take the Fermi paradox's haunting question: if the universe is so vast and ancient, where are all the aliens? Maybe we've been looking in the wrong places. Instead of searching for radio signals or Dyson spheres, what if the evidence is hidden in plain sight, woven into the cosmic web itself? Imagine a civilization billions of years older than ours, one that's graduated from planets and stars to manipulating the largest structures in existence. They might use filaments like superhighways, riding their magnetic currents like cosmic surfers, or tapping into the plasma's energy with technologies beyond our comprehension. The universe's highways wouldn't just be for travel, they'd be the ultimate renewable resource. There's even a tantalizing hint in the data. Some filaments emit strange, non-thermal radiation patterns, bursts of energy that don't quite match known astrophysical processes. Could these be the exhaust trails of unimaginable engineering projects, or perhaps markers like celestial lighthouses guiding travelers across the void? The Boots void filament, for instance, shows unexplained synchrotron emissions along its length, as if something were accelerating particles deliberately. And then there's the case of dark filaments, threads that appear too uniform, too geometrically precise, as if their turbulence has been artificially smooth. But the wildest possibility, filaments might not just be tools, they could be living artifacts. A Kardashev Type 3 civilization, capable of harnessing the energy of a galaxy, might reshape filaments like we reshape rivers, diverting their flows to build computational networks spanning billions of light years. Picture a filament as the universe's largest quantum computer, its dark matter knots acting as qubits, processing information at scales that make our entire internet look like a single grain of sand. The cosmic web wouldn't just be a structure, it'd be a mind. Of course, the skeptic's answer is simpler. Filaments are natural, and we're seeing patterns where none exist. But history has a way of humbling our assumptions. Every time we've declared something too big to be artificial, from the canals of Mars to pulsar signals, nature has surprised us. Maybe the truth lies somewhere in between. Perhaps filaments are both natural and engineered, their potential harnessed by civilizations we can't yet imagine. One thing's certain, if even a fraction of this speculation is true, the cosmic web isn't just a backdrop to intelligent life. It could be its masterpiece. And that changes everything about our place in the universe, the limits of technology, and the very definition of what it means to be advanced. The next great leap in our understanding might not come from spotting a distant planet, but from realizing the threads binding the cosmos have been humming with purpose all along. Studying cosmic filaments might sound straightforward. Point a telescope at the sky and map the thread-like structures weaving through the cosmos. But the reality is a labyrinth of technical nightmares, each hurdle more daunting than the last. The first challenge: filaments are ghosts. Unlike galaxies, which blaze with starlight, or black holes, which betray their presence with swirling accretion disks, filaments are made of ultra-diffuse gas and dark matter, barely interacting with light. To the human eye, and to most telescopes, they're practically invisible. Even X-ray telescopes, designed to detect the faint glow of superheated plasma, strain to pick up their whispers against the cosmic background. The gas in filaments is so sparse that a cubic meter might contain fewer atoms than the best vacuum chambers on Earth. Imagine trying to photograph a spider's web draped across a foggy night sky with a camera that can only see fireflies. That's the scale of the problem. Then there's the issue of distance. Filaments stretch across hundreds of millions of light years, but their width, sometimes no thicker than a galaxy cluster. This extreme aspect ratio means that from our vantage point, they often appear as vanishingly thin lines against the void, if they're visible at all. Worse, many filaments lie behind foreground objects like stars or dust clouds in our own Milky Way, blending into the noise. It's like trying to trace a single strand of hair glued to a stained glass window while standing across the street. Even Hubble, with its razor-sharp vision, can't resolve most filaments directly. Instead, astronomers rely on indirect methods, like mapping the positions of thousands of galaxies and inferring the filament's presence from the patterns they leave behind. A cosmic connect-the-dots game where half the dots are missing. Data interpretation becomes another minefield. Filaments aren't static, they're dynamic rivers of matter, churning with turbulence, magnetic fields, and unseen dark matter. Supercomputer simulations help reconstruct their behavior, but these models are only as good as our assumptions about dark matter's properties, which are, frankly, guesses. When observational data clashes with simulations, it's a toss-up. Is the model wrong, or are we misreading the observations? Take the case of dark filaments, threads predicted by simulations but absent in surveys. Are they illusions in the code, or are our telescopes simply blind to them? The answer could reshape our understanding of dark matter if we could ever confirm it. And then there's the tyranny of scale. Filaments evolve over billions of years, but human observations are snapshots, a single frame in a cosmic movie. We see a filament today, but not how it formed, how it's changing, or what it'll become. It's like trying to deduce the plot of The Godfather from a single blurry still. To compensate, astronomers use light cones, stacking observations of distant filaments whose light took eons to reach us to piece together a timeline. But this introduces its own biases. Faraway filaments appear younger, but their light is also fainter, leaving gaps in the story. The result, a patchwork narrative with more holes than evidence. The newest generation of telescopes offers hope and fresh complications. The James Webb Space Telescope peers deeper into the infrared, where cold filaments might glow faintly. The upcoming Athena X-ray Observatory promises sharper views of hot gas. Yet even these marvels face limits. Filaments emit light across the electromagnetic spectrum, from radio waves to gamma rays, but no single instrument captures it all. Synthesizing data from different telescopes is like trying to assemble a jigsaw puzzle where each piece comes from a different box. and when filaments overlap or tangle, untangling their signals becomes a Herculean task. Perhaps the greatest irony: the more we learn, the more questions arise. Every breakthrough, like the detection of faint X-ray glows along filaments, reveals new anomalies, like unexplained temperature spikes or magnetic fields stronger than theories allow. These aren't just gaps in knowledge, they're chasms. Yet each obstacle is also a clue, a signpost pointing toward deeper truths about dark matter, cosmic evolution, and the universe's hidden architecture. The challenge isn't just technical, it's a test of creativity, forcing astronomers to invent new ways of seeing. Because if there's one thing filaments teach us, it's that the universe's greatest secrets are often hidden in plain sight, waiting for the right tools and the right minds to reveal them. The future of cosmic filament research isn't just promising, it's poised to rewrite everything we think we know about the universe's hidden architecture. Later this decade, NASA's Nancy Grace Roman Space Telescope will launch with one audacious goal: to map the cosmic web in infrared light with a field of view 100 times wider than Hubble's. Imagine stitching together thousands of Hubble deep field images into a single sweeping panorama, revealing filaments too faint and distant for current telescopes to see. Roman surveys could uncover millions of previously invisible threads, exposing patterns that might finally explain why some filaments glow while others vanish into darkness. Meanwhile, the European Space Agency's Athena X-ray Observatory, slated for 2035, will peer into the superheated hearts of filaments with unprecedented clarity. Current X-ray telescopes can only detect the brightest filamentary gas, like spotting cities from space at night. Athena will be sensitive enough to see villages' faint wisps of million-degree plasma that could hold the missing baryonic matter we've been searching for. Its microcalorimeter array can measure gas temperatures with such precision it might catch quantum fluctuations in the plasma, offering our first glimpse of how the smallest scales influence the largest structures. But the real game changer might come from an unexpected direction: radio astronomy. The Square Kilometre Array, currently under construction across South Africa and Australia, will scan the sky for faint synchrotron radiation emitted by electrons spiraling along filamentary magnetic fields. Previous telescopes saw these emissions as blurry patches, but SKA's thousands of linked antennas will achieve razor-sharp resolution, potentially revealing if filaments truly spin as some observations suggest. There's even a chance it could detect the elusive cosmic dawn, the moment the first filaments ignited with newborn galaxies, captured in hydrogen's 21-centimeter line like a celestial baby photo. On the theoretical front, exascale supercomputers like the U.S. Department of Energy's Aurora are running simulations with mind-boggling resolution, tracking not just galaxies within filaments, but individual gas clouds and dark matter particles. One ongoing project, Cosmic Web 2.0, simulates filaments with 10 times finer detail than ever before, including previously ignored factors like cosmic rays and magnetic turbulence. Early results show filaments may harbor intricate substructures, thin tendrils within tendrils. That could explain why some galaxies form stars violently while others stagnate. Perhaps most thrilling are the wildcard missions. Japan's Lightbird satellite will hunt for primordial gravitational waves in the cosmic microwave background, potentially revealing how quantum fluctuations in the infant universe seeded filament formation. Private initiatives like the Breakthrough Listen project are even scanning filaments for narrowband radio signals, because if advanced civilizations exist, why wouldn't they use these cosmic highways as beacons? The coming decade won't just add new pieces to the puzzle, it'll give us an entirely new puzzle to solve. With 30-meter class ground telescopes like the Extremely Large Telescope coming online, we might witness filaments evolving in real time, watching as gas flows into galaxies or gets ripped away by void expansion. Combined with JWST ability to analyze filament chemistry, we could soon be reading the cosmic web like a history book, one that tells not just where we came from, but where the universe is headed. What makes this era unique is convergence. For the first time, we'll have X-ray eyes to see hot gas, infrared sensors to spot cold streams, radio arrays to trace magnetic fields, and computer models powerful enough to connect it all. By the 2040s, the phrase dark filament might vanish from astronomy papers as these ghostly threads step into the light. Every unanswered question, from spinning filaments to missing baryons, could find its resolution in the data flood these missions will unleash. And that's the most electrifying possibility of all, that today's greatest mysteries are simply waiting for the right tools to reveal them. The cosmic web has hidden its secrets for 13 billion years. Soon, very soon, it won't have anywhere left to hide. We've journeyed through 25 mysteries of the cosmic web, threads of dark matter weaving the universe's skeleton, filaments spinning like celestial whirlpools, and the eerie voids between them that defy logic. We've seen how these structures cradle galaxies, funnel invisible rivers of gas, and hide missing matter that should be impossible to lose. Yet with every answer, new questions emerge. Why do some filaments blaze with heat while others fade into shadow? What unseen forces twist them into braids or send galaxies sliding along their length like beads on a string? How do magnetic fields spanning millions of light years arise, and what secrets do they whisper to the dark matter flowing beside them? Consider the scale of what we've uncovered and how much remains hidden. We've mapped filaments older than stars, traced their glow back to the dawn of time, and watched them collide in slow-motion cataclysms that shape the fate of galaxies. But we still don't know why the cosmic web fragments into gaps sharper than our models predict, or how quantum ripples from the Big Bang stretched into these colossal threads. Dark matter's grip on filaments is undeniable, yet its true nature eludes us. The universe's expansion tugs at these structures, but whether they'll snap or endure is a debate raging in observatories and supercomputer labs worldwide. Here's the humbling truth: the cosmic web isn't just a puzzle to solve. It's a mirror reflecting how much we've yet to learn. Every filament holds clues to forces we can't yet name, to histories written before atoms existed, and to futures where galaxies might fade but these threads endure. The greatest lesson isn't in the answers, it's in the questions that keep us searching. So keep looking up. The night sky isn't just a scattering of stars, it's a tapestry threaded with mysteries, and the next revelation could be hiding in the glow of a filament we've barely begun to see. The universe's grandest story is still being woven, and you're here to witness it unfold. Stay curious, the cosmos is just getting started.